Okay, hello everyone. All right, so any questions before we start? We'll be going over the experiment. We'll go over the mechanism. We'll go over calculating percent yield, and then we'll take a look at two different posters from last semester, and we'll go through, how they'll be graded. Okay, does anyone have any questions? I have the chat up, so feel free to type any questions that you may have.
Hi, Dr. Hashim. I had a quick question, actually.
Go for it.
So, is the retention factor for the TLC, first of all, would there only be one retention factor, since from the video, I only saw the retention factor of the recrystallized product?
Correct, because I didn't have the standards at the time to run it against them on the TLC. They're actually included within the module. There's a page that has data, and I've included the standards within the module.
Okay. And we calculate the retention factor by dividing the product spot by the solvent front, correct?
Correct.
Okay.
Yeah.
Okay, thank you.
You are welcome.
And one more thing. Where would we find a theoretical mass and a theoretical melting point?
So the theoretical melting point, you're going to Google that. And then one of your references within the poster is where you got that value, right? So make sure you reference that. The theoretical yield, I'm going to go over the calculation. You'd have to calculate it.
Okay, so the mass and the melting point, we would just Google it, and that would be of acetaminophen?
Not like the theoretical mass or theoretical yield, it's a calculation you'd have to do. I'm going to go over that. But the theoretical melting point, yes, you could Google that. Should be 169 degrees Celsius.
Okay, and there was nothing about, just to clarify, there was nothing that we needed to know about a theoretical mass, right?
I will go over that. That is a calculation that you'll have to do. You'll need it to calculate percent yield.
Okay. Maybe.
What you need to Google is theoretical melting point. What is the actual melting point of acetaminophen, right? You should get 169 degrees Celsius. So I'll come right back to that. So let me actually. Okay, if I missed anything on the chat while I'm talking, we do have Brittany here with us that will help me follow the chat. Okay, so in this week's lab, it involved the synthesis of acetaminophen. It's the active ingredient in really hundreds of off-the-counter drugs, as well as prescription medications. You may be familiar with it from Tylenol, right? Or sold under the brand name Tylenol. But it's also an active ingredient of many different medications. In this particular experiment, it involved the synthesis of acetaminophen, starting from 4-aminophenol and reacting that with acetic anhydride. You may see throughout that I abbreviated acetic anhydride. That's that's an abbreviation for acetic anhydride. Right, and the reaction involves heating up the reaction, and that's what delta is. Now that's an example of a reaction scheme. You're showing what you started off with and what product is formed. Acetic acid is one of the byproducts that is formed, whereas acetaminophen is really our target compound. And if you're not very familiar with nomenclature, I've kind of highlighted the amino, why we call it aminophenol. The bottle says 4-aminophenol, but you've learned in organic too that that's the para position, so para-aminophenol. You could use either one. Acetaminophen, again, is the common name. We could also call it para-acetylaminophenol. You may also notice it called as acetamol. Acetamol. Oh, um, paracetamol, right? But anyways, acetaminophen is a common name. So if we wanted to think about the mechanism, because you guys will have to draw the mechanism, it is a nucleophilic acyl substitution reaction mechanism, much like what you've learned in organic chemistry too, if you recall, and you have different um, reagents that could be part of the reaction, and really the reactivity of the reagents depends on the group attached to the carbonyl oxygens. And if you recall, acid chlorides were of the most reactive because the chlorine is a very good leaving group. So the mechanism itself involves a nucleophile attacking the carbon of the carbonyl oxygen. And again, if you're ever not sure, you can always think about it in terms of partial charges, right? You have a partial negative, partial positive. Nucleophiles are electron rich, so it'll attack the partial positive charge of the carbon. Electrons will move to the oxygen, right? We know we could draw resonance within a carbonyl group. And then you'll have the nucleophile and the leaving group, and the better leaving group of the two will dissociate, and that's why it, the reactivity of those carbonyl groups depends on the substituents attached to it. And then we get the final product. So it's much like a substitution reaction. The nucleophile is being, or the leaving group is being replaced by a nucleophile. In this particular experiment, we started with acidic anhydride, and the nucleophile could attack either carbon of the carbonyl oxygens, and then this bond was cleaved, and then acetic acid was a byproduct. Now you're responsible for drawing the mechanism, and I'll take questions later about, are you able to draw it or not, and whatnot. All right, if we take a look at the actual mechanism, we're starting with para-aminophenol. You could think about it, which one would likely act as the nucleophile, the alcohol, or the amine. We know it's going to react with acidic anhydride. If you think about it, the nitrogen versus the oxygen, that nitrogen is a stronger nucleophile in this case and would stabilize that positive charge better, so it'll attack the carbon of the carbonyl group. Remember, if a bond is formed, you have to break a bond, and then you'll get the amine. The amine is now protonated to keep track of charges. That's important. Then you have the alkoxide ion that formed, which is negatively charged. All right, so keep in mind that this is the leaving group, and we know from organic chemistry that if you have an alcohol group, it's not a good leaving group. But if you have if you protonate that alcohol group, it becomes water, and water is an excellent leaving group. So what happens here is that the oxygen deprotonates the amine that's protonated, and then again, if a bond is formed, remember that a bond has to be cleaved. Right? And then you'd get the protonated oxygen, which, think about it, much like when you have water protonated, it's an excellent leaving group. This makes this, what ends up being the acetic acid as an excellent leaving group. So the oxygen would go back to reform its pi bond, and then that carbon-oxygen bond would dissociate, and you end up forming the acetic acid as a byproduct and form the actual acetaminophen, right? So mechanisms always think about what is happening, and then it'll make sense, right? Should always make sense. Mechanisms should always make sense. So here's an example of what is taking place. Okay, any questions about the mechanism? You do have to draw a detailed mechanism within the poster assignment. You will end up having to submit the file that you drew the mechanism on. I'm going to be sending an email about that. Typically, what you'll do is briefly discuss the steps of the mechanisms, or you can include it the way I included it right here, right? Simply what is happening. Any questions about the mechanism?
Dr. Hashim, I have a question.
Yeah.
Can we draw it out by hand, or it has to be through like the software or?
You do have to draw it using a software. There is one that's online that you don't have to download. I'm going to find that and send a link of that for those of you that are having trouble downloading it. It doesn't draw it. Um, it'll 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 be fine if you do it that way. But yes, you do want to use one of the softwares.
Okay, and we include the software in the references too?
No, no, you don't have to include how you drew it within the reference, but you're going to attach
Okay.
the file as well as the assignment or the PowerPoint.
Okay, thank you.
Yes, thank you. Okay, so we have our two starting material, and it's important to record exactly how many grams is weighed out, because that is used to calculate the amount of product or the theoretical yield. And then we use a recrystallize. We recrystallized the product, and that's basically to purify it, and then we use TLC to confirm the formation of the product. We didn't use it in this case to monitor the progress of the reaction, because we didn't run TLC when the reaction was midway to see whether or not the product was formed. We actually dissolved the recrystallized crystals in the ethyl acetate. So the purpose was the product formed or not. It was one way for us to confirm based on our RF values. So keep that in mind, right? And then we had the target compound. We compared it, or we characterized it based on melting point. If the experimental melting point range is narrow, meaning less than 5 degrees Celsius, and right around the melting point or the theoretical melting point of acetaminophen, then that tells us that the product was pure. If we have a wider melting point range, that tells us that the product has some impurities present within it. And then the IR helps us identify the functional groups that are present and basically characterize the product, right? Can we identify the peak or the wave number where the benzene ring occurs, where the alcohol occurs? Could we see a peak for the carbonyl oxygen, right? For the amine, and make sure you actually, within the module when we worked on IR, you can't simply put the range in general of all carbonyl oxygens. Look at carbonyl oxygens that are part of what we call an amide bond, right? That's an example of an amide bond, and those carbonyl oxygens have specific wave number range, so keep that in mind. And then we have the hydrogens attached within the benzene ring if you end up identifying those, and we have the sp3 hydrogens right here. So those are the different things that you're going to be looking at in terms of IR. So the PowerPoint, I don't post it online, but I do post this video later for you. Okay, so how do we calculate percent yields? Well, first of all, we need a balanced chemical reaction. How many moles of reactant to how many moles of products do we need, right? So if you take a look at the reaction scheme, so that's an example of a reaction scheme. What we had earlier was an example of, I actually have to go back. That's an example of a reaction mechanism, right? When we mention reaction mechanism, you're showing the detailed, curved arrows. And a mechanism, you're showing which bonds are being broken and which bonds are being formed. You're showing the detailed step within the mechanism. Right? Whereas in a scheme, you're basically showing the reactants, the reagents, and the product, right? Make sure you include heat if the reaction is being heated. This is the solvent, and remember from organic 1 and 2 that this slash means in, right? So it's basically in whatever solvent. Okay, so we take a look at the balanced reaction, and then whatever amount we start off with, the experiment calls for about 3 grams. I weighed 3.07 grams, and I measured 3.5 milliliter. Well, something to keep in mind, and then the mass of the crude product, the mass of the recrystallized product is shown. So based on the experiment, for every 1 mole of reactant, we have 1 mole of product. For every 1 mole of acetic anhydride, we have 1 mole of product as well. So it's a 1-to-1 ratio. So typically, before you run the experiment in the lab, what you want to keep in mind is what is your limiting reactant. And it's called a limiting reactant because that particular reactant will run out first, and it limits the amount of product that is formed. Hence, it is known as the limiting reactant. That was from 2046 or Gen Chem 2, right? So it's limiting the amount of reactant. So to figure out which one is your limiting reactant, you have to think about the amount you're starting off with and the amount of product that is formed, right? Whichever yields the least amount of product, whether you're calculating it in terms of moles or grams, then that's your limiting reactant. So in the case of 4-aminophenol, we weighed exactly 3.07 grams. We take a look at the 1-to-1, it's a 1-to-1 mole-to-mole ratio. And then if what we're interested in is the amount of products formed, then we need to get rid of the grams and the moles. So we're going to multiply it by 1 over the molecular weight of 4-aminophenol. And then if you notice, grams, cancels out grams, moles cancel out moles, and the only thing we're left with is the moles of acetaminophen. So if we start out with 3.07 grams of aminophenol, that's how many moles of acetaminophen will be formed. Well, in the other reactant, we're starting out with 3.5 milliliter of acetic anhydride. So we don't have grams, but we're really looking for the moles of product. But we know that based on the density, we could convert milliliters into grams, right? And the density of acetic anhydride is 1.08 grams per milliliter, right? This is the density. And then milliliters would cancel out milliliters. Well, now we end up with grams, and it's a 1-to-1 molar ratio, and then we take its molecular weight, and then grams cancels out grams, moles cancels out moles, and then you end up with the moles of acetaminophen, right? So those problems are easy as long as you know what are you starting off with, and what do you want your end unit to be in. Then it's just a matter of really figuring out what you're multiplying or dividing by. Okay, so now the limiting reactant would be whatever ends up forming less product. So in this case, the limiting reactant would be 4-aminophenol, right? You could multiply that by the molecular weight, and you end up getting the theoretical yield. Okay, any questions on figuring out the limiting reactant? You end up getting the theoretical yield. And percent yield is experimental over theoretical. We have two. We have the crude product and we have the recrystallized product. Well, the crude product we don't use to calculate the percent yield, right? Because the percent yield is the final amount that we have after purification and everything. So it would be the 2.95. So to calculate percent yield, you would take 2.95 and divide it by the theoretical mass, which in this case would be 4.26 grams. So I got 4.26 by taking the number of moles and dividing it by the molecular weight, right? Then that would give you the mass. So it's important typically to calculate limiting reactant ahead of the lab. That way, you know, would it matter if I measured 3.6 milliliters or 3.8 milliliters in the lab? No, because that was the reagent that it was present in excess, right? Yes, you could put the mole to mole ratio anywhere, right? You could have put it at the end. You know, where you place them does not matter. You're welcome. All right, so make sure you include that on your poster. Okay? You could have abbreviated this as P, as long as you mentioned what the abbreviation is. Yes, it's actual over theoretical, much like if you're calculating your grade, what you earned over what was expected, right? So experimental over theoretical. So if you're in the lab and you start out with 3.7 grams and then the experiment is done and you notice that you weighed out, let's say, 4 grams of product and you wonder what may have went wrong, calculating the limiting reactant or the theoretical yield ahead of time helps you get a sense of what you're doing. All right, any questions? Okay, so I'm gonna move on. If you have questions, you can always ask. So, and then we also have an IR spectrum. You do want to include the reference spectrum on your report. You do want to include a figure caption, whatever you call it, and the figure caption goes underneath, and then, you know, if you include the reference spectra and the experimental spectra hand in hand, and you label one A and one B, you could simply include a figure caption and mention what it is. Okay. And then we always tabulate IR data. So you will need to create a table. Okay, so I sent how you would enlarge or set up the page so that it's actually a poster. You could go on into design, slide size, page setup, and then you'd scroll down to custom 48 over 36. 48 by 36. Click OK. If you notice here at the bottom, it's 32%, right? So if I'm actually at 100%, this is how large, you know, the poster is. So then it's a good size for actually printing. All right, and then the font that you're using is 34. It's actually not small. So it's a good size. You could fit it. It's just the poster in general, when we're looking at it, should have a good flow, whether you want intro, experiment, data and result, discussion, conclusion, or however way you want to put it, like 1, 2, 3, 4, 5, 6 at the bottom. You want a good flow of the poster, right? And it should be mostly a visual. So typically what you want is less text and more of everything else. If you could say what you would like to say using a table, a figure, then that's the way it should be. Now the discussion will have, you know, a bit of text in the intro. If you take a look at the rubric that's on web courses, it'll break for you how you're being graded. The experiment methods section itself, you're simply referring to web courses and how the experiment was done, all right? I'm not expecting you to write it. You know, I'd rather you spend the time writing the intro and the discussion and the conclusion and presenting your data. So we're gonna take a look at, and then you put your first, your last name. We'll read the abstract, but Actually, we'll take a look at the data first. They have the scheme, and they call it scheme 1. Well, first of all, that's not it's a scheme, but it's the detailed reaction mechanism, right? So if you read what it says, acylation, I mean, it's wrong, but for aminophenol with acidic anhydride yields acetaminophen, right? That figure or scheme caption could have been different. They're showing the detailed reaction mechanism of, the synthesis of acetaminophen from the 2 starting materials. So maybe that would have been a better figure caption. And then if you take a look at the mechanism, there's quite a bit of missing steps, right? So the nitrogen attacks the carbonyl group. Well, there isn't that resonance showing that the electrons go up to the oxygen. That's when you fail your organic exam and wonder why, when you knew how to, the different steps of the mechanisms, is missing the little details. And then now you have this amine, and the amine is not protonated. And then you have an oxygen with a negative charge, leaving as a good as a leaving group, whereas right here it's protonated. So make sure you don't miss any of the steps. And then where would have been a better spot for this reaction mechanism is really right within the intro. It says that the synthesis of acetaminophen is typically carried out through nucleophilic acyl substitution by reacting for aminophenol. That's one way of forming the acetaminophen, as seen in scheme 1. Well, anytime you mention a scheme, that's exactly when you want to go in and input that figure, right? You input a figure or a table right where you mention it, typically in a report as well, right? So you can't say according to scheme 1, and then scheme 1 appears 3 pages later, right? And then the figure caption would have been, right below in this case, right? You'd have to adjust the font in this case. I'm just gonna take the figure caption back where it was. And then within data and results, if you take a look, it says what the mass is. It was 2.1, and then the final product was 1.43. The melting point, it was such and such. Theoretical melting point was whatever. And then they include the table, right? Well, guess what? This was just extra text to fill, space that they really did not need to include. It didn't give us any more info than what's within the table. So you definitely don't want to do that, right? Don't feel that you need to write more to get a better grade, right? Definitely don't do that. There's a lot of things that you could do that would make it, easier on you. You could include the melting point right there, and then really don't need to. If you kept it at the bottom, it would be 166 to 169, and then you have the degree Celsius, right? Okay, well, you have the product, the mass, the melting point, crude, recrystallized, theoretical. Well, I could have, oopsie, I need to add another line. I wasn't sure. Anyways, they could have moved that theoretical down right after recrystallized, and then input what your theoretical mass should have been, right? And what the theoretical melting point would be, right? And typically we just put a dash, not an X if something is missing. But those are just little things, not necessarily that you'd get points off for, but you could make your life easier, right? And then in this case, I would move out. Okay, so mass and melting point of products. There was only one product, right? There wasn't really 2 products, crude and recrystallized product. Anyways, the TL, and then it mentions about the TLC. RF values, starting material 0.7, 0.6 for the product, and 0.6 for the recrystallized product. It could have been text, it could have been a table. Again, think about it that it's more of a visual, that someone is more likely to look at a table and read the table caption and know what's in the table than decide, where to start reading within the text. So if you could take the data that you have and put it into a table instead of text within your data and results section, then definitely do that. And don't feel that you have to do it both ways, right? There's no point of doing it both ways. Anytime you put in calculation, you have to indicate what you're calculating. If I'm looking at this, calculation, I have no idea what am I looking at? I wouldn't necessarily, switch it into the chemical formula. I would have just used an abbreviation of each product and what it was, and it would have indicated what it was. You don't need to include that, right? Because for someone that's looking at it now, they're perhaps not sure what those are. And it doesn't have proper figure caption. Okay, so it says percent yield was obtained and shown in the calculation below, and the results in a yield is such and such. So I mean, it kind of mentions what this calculation is, but looking at the calculation, I may have got confused and not even read this. Okay, so I mean, in an actual poster when you're looking at it, so make sure everything is clear. Use less words if you can. If you want to recreate a TLC for this poster, you may, or if you want to use the one from web courses, you may as well. The difference is that you guys will also include IR here, so you'll have a table with the IR data and you'll have 2 IR spectra. Okay, any questions about data and results? Brittany, do you want to add anything on the data and results?
I don't really have anything to add.
Okay, perfect. Wayne, I just saw the message from Wayne asking about theoretical mass. We just did the calculation of how you calculate theoretical mass. All right, you take what the amount it's actually shown on here as well, but you'll be able to watch this video later to calculate theoretical yield. I'm going to go back to the intro. One of the most recognizable drug, Tylenol, perfect. And anytime you reference something, you're going to include it as a superscript. And if we go to the bottom of the page, here is the reference that they're referring to, right? Perfect. And then Tylenol, which has the trade name, acts as perfect, all right? And then the synthesis of acetaminophen is typically carried out through nucleophilic acyl substitution reaction, perfect, by reacting for aminophenol with acidic anhydride, right? You could include acene in, I just put comma and scheme 1, right? And then you'd have the figure caption. Typically, you'd include a little bit about what is happening within the reaction mechanism briefly. And then in this experiment, a variety of lab techniques were used to accomplish and confirm the synthesis of the acetaminophen, such as TLC, recrystallization, and melting point analysis. Well, you kind of want to write the statement of what is happening here, but This would definitely not be it. I would honestly remove this and change the way it's written, right? But I'm gonna move on. Wait, definitely don't want to write it this way. Then layer chromatography is a technique. Well, if you mention that, why you're using TLC, and then you could mention what would TLC do. TLC is a technique that allows you to determine if the product in question has formed, and allows you to measure the time taken to reach that standard product. Okay, well, how? Well, if you read following that, by comparing the retardation factor of the newly formed product to two standard RF values. Which two standards? The experiment or the chemical reaction can be determined. It could definitely be worded, and then RF values also depends on the interaction with each molecule and the stationary versus mobile phase. There's different things that you could write. It's just going to be very short in few sentences, right? Depending how you reword it. How to calculate RF value could have been included here, and it could stay right within the data and discussions section. That's fine. And then they say, since 3 spots were used, 3 spots should be observed, right? That's not necessarily true, right? Because, if you're spotting the starting material, the product, the experimental product, and you get, more than one spot, it could tell you that, and if more than one spot doesn't necessarily match the reactant or the product, it could tell you that you have other side products present. It says 3 spots should be observed when the reaction is complete. Kind of, in this case, but it really depends. Sorry. Okay, so you could change that. It says any observation of 4 spots indicate that the reaction is incomplete. Really depends, right? In this case, it's not clear. And not to mention that in this experiment, TLC was simply used to confirm the formation of the product by comparing the RF value with the standard. Okay. And then it says melting point was utilized to confirm the identity of the product. You are confirming whether or not the product is pure and not related to identity, right? We're characterizing it by melting point as well as IR, right? You don't have to mention that you're comparing it to theoretical standard. You could include the theoretical standard here or later. It doesn't really matter. And then a general statement of the purpose of this entire, project or experiment. It was right here within the highlight, but it could have been rewritten. And if you ever include abbreviations, you don't need to. In this case, it should have just been TLC, the abbreviation, because that student already included the abbreviation. So just keep that in mind. Okay, Brittany, do you have any comment on the intro? Okay, so now, yeah, go ahead.
So I mentioned this in the meeting that I held and posted as well, but just to be careful and make sure that the students know the difference between a scheme and a reaction mechanism. And to also make sure you have your in-text citations for anything in the introduction.
So yeah, anytime you have, you use a reference, we showed it'll be within the reference and you'll use a superscript, right? And within the PowerPoint, we mentioned the difference between a scheme and a mechanism, right? That's a detailed mechanism that includes the arrow. A scheme is simply the reactant being converted into product, which really you could include the mechanism within data and results, but it's really not data and results. You could include both scheme and mechanism within the intro or somewhere within the poster. That's really up to you. The mechanism sort of includes both. All right, and then the discussion really tells us whether or not you understood what was taking place, whether or not you know what the data means. So you're basically taking the different data that you've included and you're discussing the data. It's not similar to what's included here within that text, that the mass is such and such and for the recrystallized product is such and such. You're more so explaining it. Do you have to explain every single data point that you get? No. Do you have to explain how you got to calculating theoretical yield? No. If you mention, do you need to mention the mass of the crude product, for instance, within your discussion? No, not unless you'd like to say that when it was recrystallized, the mass was less, which may have meant that there was impurity presence and recrystallization further purified it, right? So make sure any data that you include within the discussion, that you're actually discussing it and not simply listing it, right? So this discussion says the initial TLC plate revealed a successful reaction because the product standard RF value and RF value of the experimental recrystallized products were the same. It could definitely be reworded and made simpler, right? You could say the same exact thing using one line instead of 2.5, right? You could say that the experimental RF value, the RF value of the recrystallized product was, 0.6, which is consistent with the theoretical, or which is consistent with the standard, right, given. And then you could refer to the table where you included the RF value of each. So feel free to refer to the tables within the discussions, right? And then it says, since only one spot was observed, then it was complete. Well, they already mentioned that the TLC, the RF values was indicative of the formation of the product. So they don't need to mention that one spot, right? It's kind of the same thing. So this is an example of discussing your data because you're telling us what does it mean to have both RF values being the same. And this kind of repeats the other one without including RF values. It doesn't give us any extra insight. Okay, should they mention about recrystallization first or RF value? When you discuss your data, you kind of want to go in the order of what was done. So you don't want to discuss the TLC and then go in and discuss recrystallization. And the same sorts of apply when you put your data and results. You don't want to put the final outcome. Remember, it's a flow of what's being included. So someone that's looking at it is going to see the mass of crudes, recrystallized, TLC, and then IR, right? So when it could vary within the data and the results really, but in the discussion, make sure you kind of have that flow of what you're choosing to discuss first, right? If you already told me that the product was formed, I might not want to read about recrystallization at this point. Whatever you can write to make it simple and to the point, do so, right? Right, so things like that. I'm gonna move to the conclusion. In the conclusion, you do want to pick a set of data that you're comparing and confirming that the experiment, that the product that you were intending to synthesize was indeed synthesized. So if you opt to discuss in terms of melting point, then do include the melting point of the theoretical melting point of acetaminophen and the recrystallized, right? Since you guys didn't actually run the experiment, I'm not expecting you to be able to come up with experimental errors. But here it says this could be, the experimental error could be due to not allowing the crude mixture to cool completely. That's when it initially recrystallized. That wouldn't really be a, you know, a source of error. If it wasn't cooled completely, or if it was cooled too quickly, then the product would have some, you know, a whole lot of impurities within it. But then when it would be recrystallized, that would take care of that. So sometimes those are not good sources of errors, but you guys don't have to worry much about that then, since you're not running the actual experiment. There's a lot going on. All right, they do include the IR of the reactant and product. They're missing the tabulated data of DIR and what DIR means. The intro, notice this is actually a scheme, not a figure. I mean, it's sometimes called a figure, but a better way would be a scheme. You do want to include heat, the solvent system. If you read, you know, I'm just going to read right here. A TLC plate was used to analyze the recrystallized acetaminophen. What exactly is the purpose of TLC? Are we analyzing the recrystallized acetaminophen? Could there be a better term? This involved using a TLC plate, and TLC plate used to analyze? And then they say again, it was a group project. This involved using a TLC plate and UV light in order to find the RF values. Does this statement really explain, you know, the purpose of using TLC, right? And then it goes further, which represents the distance traveled by the analyte on the plate divided by the solvent front. Does that tell us anything relevant to someone that doesn't know much about TLC and is looking at your poster, right? And it seems like this person copied and pasted from a different poster. It says in order to produce NBS, right? Make it simple, make it straight to the point. You don't have to include, you know, a whole lot of info, but you definitely want to make sense. The way you write tells us whether or not you know what you're talking about. So this was not a great poster. Do they need to include a figure of the melting point? You know, definitely not. That's irrelevant in a way. But they could have. You're not getting points off for including that. And then the data revealed that the substance, and I mean, again, it was a group project and both groups had a melting point close to that of the expected melting point. Not bad. This means that the products were made were pure. Yeah, when you have a close, narrow range, it indicates that the products are pure. When looking at the TLC plate, it could be seen that in one reaction, the starting material has been fully consumed, and in the other TLC plate, that some product remains, and they kind of drew that in, but didn't mention much about the IR or analyzing the IR either, right? In the conclusion, you restate briefly the purpose of the experiment, and based on the results, the experiment was successful, and they concluded that it was successful based on the melting point, and the melting point being close to theoretical value. You could definitely also refer to the IR spectra. Okay, so any questions?
I have a question about the IR.
Yes.
So do we need two IR spectrums, but only one table, right?
Right, yeah.
And the first IR spectrum is of our reactants, so we're seeing like what functional groups were lost and.
So we actually don't have the IR of the starting material. It would be a reference spectra, how the spectrum would have actually looked like.
Oh, so it's like comparison.
Yeah, or if you didn't want to post like the reference spectra, the actual image of it, do include it within the table at least. Right, so when we're looking at the table, we can compare the spectra of the actual data and those wave numbers to the one of a reference spectrum.
Oh, okay. And then I have a question about the TLC too.
Yes, what about it?
In the video of the experiment you did, there was only one spot recorded. So do we have to include the product spot and the starting material in a new figure?
No, I included the data for those on one of the pages on web courses within the module. I don't have the actual, I didn't actually run it on that TLC plate, but the
so
RF values, yeah, you can include it like in a table with RF values, and next to it you could put the image, or not put the image at all as well, that's fine. Or you could do like what this group did and kind of draw them in.
Okay, thank you.
Yeah, you're welcome. Okay, any other questions?
Yes, Dr. Hashim, I have a question.
Go for it.
So by reference spectrum, are you referring to a spectrum of the reactant? Because the poster you currently have up, it's displaying in the data and results section one spectrum for the reactant and then one spectrum for the product.
No, I mean going to like the data bank that we used earlier in the term on week 2 and looking up the spectrum of the products, acetaminophen, and using those data as the reference spectra for the product.
Oh, okay, so comparing the spectrum for the product that was obtained during the experiment to one from the data bank.
Perfect.
Okay, all right, thank you.
You are welcome. All right, and if you guys submit or create an early draft of it, a complete draft, and you want me to take a look at your poster, you could most certainly email it to me and I'll comment on it for you. Right, but it'll have to be well ahead of the due date. A few days at least. All right, any questions? I meant to show you how you create the actual poster, but all you have to do is go in and insert text boxes, right? And however way you want to lay out the poster, go in and insert different text boxes. Okay, I'll probably have another office hours sometime early next week for this poster in case someone has any questions or
There was another question.
Yeah.
Are they submitting it in PDF or in PowerPoint?
So what we did last term is that they submitted both, just because sometimes it's easier for us to grade it when it is in PowerPoint. It'll mention, right? But it'll ask for both PDF and PowerPoint. Okay, any other questions?
Somebody asked if we only need the IR of the product, the experimental product, and the reference.
Correct, yes. Those would be the only two.
And she said we don't need to compare the reactant spectra with the product spectra.
No. There are some peaks on the product, right? On the IR of the product that wouldn't have been on the IR of the starting material, right? If you wanted to use that within the discussion, that's an option. But comparing it to a reference spectra is another way of discussing the data, right? As long as you identify which, peak corresponds to which functional group, and then it matches a reference spectrum. But yeah, definitely within the discussion, you can mention the appearance of the carbonyl group that wasn't present in 4-aminophenol. And then you have the sp3 hybridized carbon hydrogen stretch as well. Okay, so okay, I will